Okay, so let's move to the first question. First question is to find the rank of the given matrix. So how we will find the rank of the matrix? First we will see, we will find the row reduced form or row reduced echelon form of the given matrix. Okay, basically what we are doing is how many independent rows are there, or the same way we can do for columns also. Okay, so how many independent rows are there? So that is actually the rank of the matrix. That is the one way to do. Otherwise what we will do is we will take the all kind of sub matrices, like it is a 3 by 4 matrix, so we can consider all n by n matrices like 3 by 3, 2 by 2, 1 by 1, like. Okay, what is the maximum? Means if 3 by 3 matrix or 3 by 3 matrix sub matrix, if the determinant is non-zero, then that is the rank. Okay, otherwise we will go to the lower level 2 by 2 and so and so. So the easiest way is to do the row reduced form. So we will see for the first question how we will find the rank of the given matrix. So first we have the matrix A. We will do the row reduction to the, this is the symbol for equivalence. Okay, so row reduction means first we will keep the row itself 1, 2, 0, minus 1, and for the second row what should be the operation? Can you tell what is the operation?
R2 minus 2 R1.
Yeah, R2 minus 2 R1, and in the same way R3 should change to R3 minus 3 R1. Okay, so we will get 0, 2, minus 3 and minus 1, right? And in the same way we will do for the second one. Minus 2. Okay, now obviously we can see the R3 is actually the multiple of the R2. Okay, so if we are doing in the next step, if R3 changes to R3 minus 2R2, we will get 1, 2, 0, minus 1, 0, 2, minus 3, minus 1, 0, 0, 0, 0. So from here we cannot do further reduction. One thing we can reduce is we can divide the second row with 2 and make the coefficient as 1. Okay, like that we can do. Other than that we cannot make the first two as independent, sorry, dependent thing, right? The first two are independent rows. So here we can conclude that rank equal to 2. So these two, corresponding to these two, we will count. These are the independent rows in the row reduced form. So rank is 2. Option C. Okay. Now let's go to the next question. Here the question is, we have given a system of equation, 3 equation in 3 unknowns. We need to check how many solutions exist for this system. Okay. For that, the best way is to write the given system in a matrix form. How we will write in the matrix form? This is 1, 1, minus 1, 2, minus 3, 1, 1, minus 4, 2, times x, y, z equal to 0, 0, 0. So this is something in the form Ax equal to b. Okay, so this is in the form the matrix. So if we are multiplying a with the x, then we will get the given system. Okay, now to find this number of solution, what we will consider is the augmented matrix AB. Okay, what does the augmented matrix means? We are just concatenating the B together with the A. So 1, 1, minus 1, 0, 2, minus 3, 1, 0, 1, minus 4, 2, 0. So again what we want to do is we will reduce this system. Okay, so if we are reducing 1 1 minus 1 0, what we will do, R2 will change to R2 minus 2 R1 and R3 should change to R3 minus R1. So basically our aim is in the first column make all the entries 0 except the first entry. So that is our intention. That is why we are doing this kind of operation. Now R2 minus 2 R1 means this will be minus 5, 3, this will be 0, and R3 minus R1. Okay, again here in this case also what we got is this is equivalent, not equal. Okay, again the second and third row are same. So in the next step what we can write, 0 minus 5 3 0 0 0 0 0. Now here every time what we are doing is, this is not a single matrix, this is an augmented matrix. So write it separately like this. Now here, from here, what is rank of A and what is rank of the augmented matrix AB? Can anyone tell what is rank of A?
2.
Rank of AB means augmented matrix?
2.
Both are 2. Okay, so the system has a solution if rank, both the rank means rank of A, rank of AB are same. Okay, if they are not same, we know there exists no solution. In case if it is a non-zero value, we don't have a solution. Okay, so here we have a solution. Now can you say whether it is a unique solution? Question is whether it is like no solution, unique solution, infinite solution, finite but more than one solution. So which option is correct in this? No solution is wrong because we have solution, or from the system itself we can see trivial solution, 0 0 0 is a solution, right? So solution is there. Is that unique or infinite or finite? Okay. Now that is why we are having, so rank of A, rank of AB both are equal means there exists a solution. Also if it is less than number of unknowns, which is 3. Okay, here we have 3 unknowns x, y, z. Okay, this value, the equal value is strictly less than number of unknowns. We have infinitely many solutions. So for any given system, we have only 3 options. One is no solution. No solution means rank of A and rank of AB are different. In that case, no solution. And the next case is rank of A and rank of AB equal, and this is equal to number of unknowns. Okay. In that case, we have unique solution. And the third case is rank of A and rank of AB are equal but strictly less than number of unknowns. In that case, we have infinitely many solutions. And not that in any case we have these 3 only. There is no case which has finite number of solution. Okay, either unique solution or no solution or infinite solution. In any case, we will not occur with a system with finite solutions. So for example, what we are having, so this is the final matrix obtained. So this is equivalent to the given system. That means we can write it as 1 1 minus 1 0 5, sorry, minus 5 3 0 0 0 into x y z. So we started with the one matrix, we reduced the n matrix. So for the easy calculation, we will use the reduced matrix now. From this, what we know? X plus y minus z equal to 0 minus 5y plus 3z equal to 0. So that implies 5y equal to 3z or y equal to 3z by 5. Now we can substitute the value of y and z in equation 1. So it will be minus y plus z. So minus 3z by 5 plus z. So you can do the calculation here, whatever. So what we are getting? We are getting x and y in terms of z. And this z can be varied to any real number. Like z can take 1, 2, 0.5, anything, right? So z have infinitely possibility. So like how much ever possibility z is having, that much ever possibility we are having for our solution x, y, z also. So that is why the solutions are becoming infinite in number. Is that clear for everyone? So infinite solution. Okay. 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 If you have a doubt, you can ask. Otherwise, we can go to the next question. Okay. What is the next question? Next question is given A is a matrix and given some 4 equations in A. So which one is true? That is the question. So either you can find a square, a cube and substitute in each of these and check which one is true. But we have already studied what is characteristic equation, correct? So, and we know if for a matrix what is the characteristic equation or characteristic polynomial, and that particular matrix will satisfy that characteristic equation. So it is enough to find what is the characteristic equation of A. How we will write the characteristic equation? Determinant of A minus xi equal to 0. Correct? Now, what is this value? So this will be a polynomial, okay, a polynomial in x. Now a minus xi means what we will do? A is the given one, xi means x multiplying with identity. That means along diagonal we will have x, all other point it is 0. Okay, so we will get this 1 minus x 0 0 and 1 2 minus x 1 2 3 2 minus x. So what I am doing is along the diagonal I am just doing the minus x which is coming from the minus xi. Okay, 2 minus x. So what we want to do is equate this characteristic equation or polynomial with the 0 and find the determinant. Okay, so what is this? 1 minus x into 2 minus x square minus 3. Okay, and the remaining other two will be 0 because the next two terms are 0. So this is equal to 0. So 1 minus x into maybe I will write the final answer. So if we are just expanding this and all, what we will get is x cube minus 5x square plus 5x minus 1 equal to 0. So you can just calculate this, you can do the calculation yourself. So this is our characteristic equation. Now what is the thing? We have a theorem called Cayley-Hamilton theorem. It states that every matrix satisfies its characteristic equation. Its characteristic equation. That means instead of x, if we are giving the matrix A, it will satisfy. That means a cube minus 5a square plus 5a minus I. Instead of 1, it will become I, the identity. Okay, it will be equal to 0. 0 means the 3 by 3 matrix 0. Okay, so here it is a polynomial in x. When we write in matrix, we have to replace everything correspondingly. Okay, instead of x, we will replace with the matrix A. So 1 should be replaced with the identity I, and 0, the number 0 should be replaced with the matrix 0 matrix. Okay, So a cube minus 5a square plus 5a minus I, B is the option. Okay, so in this way you can find it, or as I said earlier, you can separately find a cube a square. That is a bit complicated, and substituting everything, that is complicated. So this way you can do it. Fine. Any doubt in this question?
No, ma'am.
Okay, now this question is basically, I just want you to, maybe you may be knowing because the proof is already covered in the class. If we have the eigenvalues, okay, of the matrix is given, okay, what is the eigenvalue? Eigenvalue means?
Roots of the characteristic polynomial.
Yeah, roots of the characteristic polynomial. So here we got some equation, right? X cube minus 5x square plus 5x minus 1 equal to 0. So it will have 3 roots. So that is called the eigenvalues of the given matrix here. Here the question is given, A is the matrix of order 3 by 3 and the given the eigenvalues 3, 4, 5. So the question is to find the determinant of A. Using the eigenvalue, we have already seen in the class what is the relation between determinant and eigenvalues. I will just take these two results. I am not going to prove. Determinant of A equal to, so this is a very standard result, product of eigenvalues and trace of A equal to sum of eigenvalues. The proof is not that difficult, but the thing is it is a kind of a bit machinery, like you have to equate two side and what is coming means both side equating and all. So maybe you can check in the lectures or anywhere, like you can Google or anything. Proof is not that difficult, and this is very standard. You should remember these two things. Product of eigenvalues is determinant and sum of eigenvalues is trace. So here it is given the eigenvalues 3, 4, 5. So what is the determinant of A? 3 into 4 into 5. Okay, that is 60. Option A. Now, so using the eigenvalue, if we know the eigenvalue, we can somehow predict what is A, like whether A is singular or non-singular. If 0 is an eigenvalue, obviously determinant of A will be 0. Okay, in that case we can say A is a singular matrix. If every eigenvalue is non-zero, obviously determinant of A is non-zero. In that case we can say A is non-singular. Okay, conversely, if determinant is non-zero, we can say we have all eigenvalues as non-zero. In the same way, if determinant of A is 0, at least one eigenvalue is 0. So, like that we can relate with eigenvalues and determinant. So, the next question is just similar to this. Here we are finding what is the given the eigenvalues 1, minus 4, 5, and the question is what is the trace of A. Trace of A by definition, I hope you know that. Trace of A means sum of diagonal entries. Okay, we know what is diagonal entries. So, sum of the diagonal entries is trace of A. So, we have the result, trace is same as the sum of eigenvalues also. 1 minus 4 plus which is equal to 2. Okay, this is just the application of this two result. There is nothing more in this question. So, I hope we can go to the next question. Okay. This is also a comparatively simple question. The question is given the matrix and in the matrix we have two variables k, k square, one variable k, and at two places we don't know what is the value of k. We need to find the value of k such that the rank of matrix is 2. Okay. So, what we will do? We will reduce the matrix to possible form. So this is 1 1 1 1 and R2 will change to R2 minus R1. And R3, because 5 should become 0, okay, R3 should change to R3 minus 5R1. This is k square minus 5k. Okay, now in the next step, what we will do? This 2, this we need to make 0. Okay, 1 1 1 1 0 1 minus 2 k minus 1, and for that we should change R3 to R3 minus 2 R2. 2 minus 2 0 k square minus 5k minus 2 times k minus 1. Okay, what we want? The question is find the value of k such that the rank of the given matrix is 2, and we got this is the final reduced form. Okay, so what should be the k? How you can find the k? Rank should be equal to 2. So first two, obviously first two are non-zero rows. Rank 2 means only 2 non-zero should be there. Third one should be 0. Okay, third one should be 0 means the value here k square minus 5k minus 2 times k minus 1. It should be equal to 0, right? Rank equal to 2 implies, so we need to find the condition on k such that rank is 2. So we are starting with rank is 2, so that what should be the k? What can be the k? Okay, minus 2k plus 2 okay, I think some mistake. Yeah, 1 minute, there is some mistake then.
5k.
It is 5,
Exactly
right?
5.
And it is just 5, not 5k. Okay, so we were doing R3 minus 5 R1. So 5 times 1, so it should be 5. So k square minus 2k minus 3 equal to 0. Okay, now we can solve the equation. We can write it as k minus 3 into so what are all the possible values for k? K equal to 3 or k equal to minus 1. So if we are having k equal to 3 or k equal to minus 1, the last entry, okay, 3 3, okay, a3 will be 0, so rank will be equal to 2. So out of the option we have only 3 is there, both 3 minus 1 is correct, so from option we can conclude it is 3. Okay, okay, now this is okay, this is just similar question. You can just by looking at this, examining this, you can say whether this have unique solution or no solution or infinite solution. Can anyone tell very quickly? It's just a 2 equations. Can it have a solution? That is the question. Any idea? Here either you can do the similar way, like write the matrix, augmented matrix, solve it and all, but just see the LHS you can see 6x minus 3y. It is actually 2 times multiple of the first equation, right? 2x minus y. But is it true for the RHS side? Let me write 2x minus y equal to 1. So this is our first equation. So 1 into 3. That implies 6x minus 3y equal to 3. Okay, so that is what we are getting from the, actually this 1 and whatever I have written here too, both are same. This is just a multiple of 1. And what is the next one? 6x minus 3y equal to 12. Can it happen? So these are our two equations, 2 and 3. Is this possible? No, right? Because 6x minus 3y, both side LHS is correct. 6x minus 3y equal to 3 and 6x minus 3y equal to 12. But these two are not true. Okay. So this is a kind of mismatching situation. 6x minus 3y equal to 3, 6x minus 3y equal to 12. Both will not satisfy together. If one is satisfied, another will not be satisfied. Okay, and vice versa. So this system is inconsistent. That means there is no solution which satisfy both the equation. Okay, so just by examining like this, if it is just two equation and all, you can see whether it is follows something very quickly. Otherwise you can do in the I will very quickly do that augmented form also. 2 minus 1, 6 minus 3, this is our A, and we are just attaching the B, 112. Okay, now we will do R2 to R2 minus 3R1. 0 and 12 minus 3 is 9. So what is the rank of A here? Rank of A is 1 because this is our A or something equivalent to A. Okay, some A dash or something we can write it. So correspondingly equivalent, this is our B dash something. Okay, so A dash B dash is the one corresponding to the augmented matrix. So rank of A means we have only one non-zero row. Okay, at that time the rank of A is 1. But what is rank of AB? Can anyone tell?
2.
2, because for AB together, if we are considering, we have two non-zero row. If we are considering A only, one non-zero row, together means we have two non-zero rows, correct? So rank of A and rank of AB are distinct. That implies no solution or inconsistent system. Inconsistent system means there does not exist a solution for the system. That means there does not exist a xy such that it satisfies both the equation. Okay, I hope it is clear for everyone, or if you have doubt, please ask it. Again an equation which which uses the characteristic equation concept. Here also it is given for a 2 by 2 matrix. The equation is given m square minus lambda m plus 2i equal to 0. Obviously the matrix M should satisfy the characteristic equation, correct? So either we can find the characteristic equation or you can substitute the value m square minus lambda m plus 2i equal to 0 and equate the equation, find the lambda. That is one way. Or find the characteristic equation of m and equate it to this m square minus lambda m plus 2i and find the lambda. Okay, let us do that. So to find the characteristic equation, what we will do? 3 minus x minus 2 minus 2 minus x. This determinant should be equal to 0. That means m minus xi equal to 0. From here 3 minus x minus 2 minus x plus 8 equal to 0 and okay. So we got the characteristic equation x square minus x plus 2 equal to 0. So our matrix M should satisfy m square minus m plus 2i equal to 0. Okay. Now comparing these two, what is the value of lambda?
-1.
1, right? Because it is m square minus lambda m plus 2i and m square minus m plus 2i equal to 0. Okay. So lambda equal to 1. Fine. Okay. So you can do like this, or you can do find the m square lambda m plus 2i and equate it like each for entry and find the lambda. That is also a possible way. Here that will also be a not a difficult thing because m is just a 2 by 2 matrix. Okay. This also just uses a one concept that we have already seen in the class. So given the rank of the matrix A 7 by 5 is 5 and the matrix B 5 by 7, that means order of B is 5 by 7, its rank is 3. So what is the utmost possible rank of AB? AB means AB, A is a 7 by 5 and B is a 5 by 7 matrix. AB is a 7 by 7 matrix, right? Okay. Now, what is the rank of AB? At most, okay, it can be anything, we don't know exactly. With the given information, we cannot find what is the exact value of rank of AB, but we can say it will not be more than this value. So, do anyone knows how to find that one? Like we have one result, the rank of AB is less than or equal to something. Anyone remembers? Rank of AB less than or equal to minimum of rank of A, rank of B. Okay. So this is a result. If we are having a product AB, okay, then rank of this product will be less than or equal to rank of A and rank of B. Now, we already know from the question rank of A is 5 and rank of B is 3. So, it should be less than or equal to minimum of 5 and 3, which is 3. Okay, so even though AB is a 7 by 7 matrix, we got a very good bound for the rank. Rank will not exceed more than 3. It can be 3, it can be 2 or 1, something like that. Okay, rank of AB is always less than or equal to 3. So this is the answer, but we cannot conclude what is the exact value. Now, if we are going to the next question, we can conclude the exact value of the rank of AB. Okay, here we are having some extra condition. Okay, not this question. Okay, to that question we will come to later. Okay, before that we will do the 10th question. Okay, this question. Okay, first let us do this question, then it will be easy to understand. Again, we are having two matrices A and B. Okay, both are given square matrices of order 7. That is, both are 7 by 7 matrix. And A is non-singular. Earlier we have got some matrix. We don't know whether it is non-singular. Actually, it was not even an invertible matrix. It was like order 7 by 5, something like that. Here it is 7 by 7 square matrix and it is given A is non-singular. That means A is invertible. And given rank of B is 3. B is a 7 by 7 matrix but rank is 3. Question is, what is rank of AB? As earlier, can you tell what is an upper bound for rank of AB? Rank of AB should be less than or equal to, what is that? What was the result? Rank of AB less than or equal to? Minimum of rank A and rank B. Now, what is rank of A? Rank of A. Rank of B is given here. Rank of B equal to 3. It is given in the question. Okay.
7.
Yeah, 7. Very good. Rank of A is 7. What is the reason given? A is non-singular. Like explicitly they didn't mention rank is 7, but since it is non-singular, what does that mean? So determinant is non-zero. Determinant is non-zero means all the 7 rows are actually independent. Okay, the collection of rows or collection of columns if we are taking, they are actually independent. That is exactly same as rank is 7. Okay, so non-singular and rank is like a full rank. Both are the equivalent concept. Now, here from this, now what is this value then? Rank of AB less than or equal to 3, right? Rank of A is 7, rank of B is 3. So, minimum of 7 and 3 is 3. So, we got rank of AB is less than or equal to 3. But the question is, what is rank of AB? Again, since the A is non-singular, we can use the condition of the non-singularity. A is non-singular means A has determinant non-zero or A is invertible. That means A inverse exists. What we want to find a rank of AB. Let us start with the rank of B. Rank of B we know it is 3. Okay, again rank of A inverse AB. I can write like this, right? Because A is invertible, so A inverse is well defined and A inverse of A is identity. So B is IB. IB means A inverse A B. Okay, this step is clear, correct? Now, from here, how can we use this condition? That means product is less than or equal to minimum of the separate matrices. Okay, if I am taking A inverse as one matrix, AB as one matrix. Why I am taking like this? We want the rank of AB. We got an upper bound for rank of AB as 3 from here. Now, from here we are going to find a lower bound for the rank of AB. Okay, so this should be less than or equal to minimum of rank of A inverse rank of AB. Okay, now it is not needed, but still I am asking what is rank of A inverse? Just to check whether you understand the concept. What is rank of A inverse? Is A inverse invertible? We have already seen A is invertible. Okay, for invertible matrix, what we have seen, all the 7 rows or all the 7 columns are actually linearly independent. Okay, and in that case, like whatever row reduced form we are writing, we will get all the non-zero rows. All the rows are non-zero rows because nothing is dependent on other. So this kind of like row operation will not cancel any row. So all 7 non-zero rows we will get. So rank is 7 in that case since A invertible. The same goes to A inverse also, right? A is invertible, obviously A inverse is also invertible because A is the inverse of A inverse, right? So A inverse invertible means A inverse has rank 7. A inverse invertible means its determinant is non-zero. Its determinant is non-zero means all the rows are independent. Okay, the set of all rows is independent. That means if we are doing the row reduction to A inverse, we cannot get a row as 0 row. Okay, because one row is not dependent on others. Correct? So what we can conclude, we will get a full rank for A inverse also. Okay, so rank of A inverse will be 7. Rank of A is 7, rank of A inverse is 7 because A is invertible. Now, here this is minimum of rank of A inverse and rank of AB. Now this minimum value is obviously should be less than or equal to rank of AB, right? What I am taking? I am taking a minimum between rank of AB and rank of A inverse. Actually no need to check rank of A inverse, whatever rank of A inverse. This minimum of rank of A inverse and rank of AB is less than or equal to rank of AB. Okay, so what we got? We got a lower bound 3 for rank of AB. So this is first equation, this is second equation. What we got? 3 less than or equal to rank of AB from the second equation. And from first equation what we got? Rank of AB less than or equal to 3, right? So basically what is rank of AB? Is 3. Okay, so here we wisely use the invertibility of A. If A is not invertible, we cannot say something for this lower bound. Obviously the upper bound 3 we will get. Okay, but to get this lower bound, we have nicely used the property of invertibility of A. Is the question answer clear for everyone? Any doubt? Anyone have doubt in this one? Okay, so I think we can go to the next question then. Now the next question is, I hope the last question is clear for everyone. Now the next question is, what is the largest possible value of the rank of A and the smallest possible value of the nullity of A if A is a 5 by 3 matrix? Actually we have seen the rank, nullity, all these things for a linear transformation also. Basically both of these concepts are equivalent. Okay, for example any linear transformation we can write in a matrix form, and any matrix we can write it as some kind of linear transformation. So both are equivalent. So the concept rank, nullity, everything are same actually. Okay, now the question is, what is the largest possible value of rank of A and the smallest possible value of nullity of A if A is a 5 by 3 matrix? If we are given just one matrix, rank of A will be less than or equal to minimum of Mn if A is an M by N matrix. Okay, means what we are doing, either we are doing through the column wise operation, row wise operation, or the column wise operation. Like we will reduce A row wise. At that time what we will get? Obviously number of non-zero rows will be strictly less than the total number of rows M. Okay, and if we are doing column wise, similar way. Okay, number of independent columns or number of non-zero columns is strictly less than total number of columns, which is equal to n. Okay, so obviously the rank should be less than m and less than n. These two conditions should be satisfied. So that is why if A is an m by n matrix, we know rank of A is less than or equal to minimum of m and n. Okay, now here A is a 5 by 3 matrix. So what can be the upper bound for rank of A? Anyone?
3.
3. Obviously it should be less than 5, it should be less than 3. So it should be less than or equal to 3. Okay. Now in the case of matrix also, we have a rank nullity theorem which is same as the our rank nullity theorem we have seen in the transformation. What does that mean is, if A is a matrix, rank of A plus nullity of A equal to number of columns. Clear? Now again, can you guess what does this mean by nullity of A? You have seen what is nullity of a linear transformation. Nullity means the dimension of null space, where null space is the set of all elements which maps to 0. That is our null space. Okay, in case of a matrix, what is the null space? Here also the same concept, set of all x such that ax equal to 0. Okay, earlier it was like instead of a we have a linear transformation. As I told, linear transformation matrix both are like means equivalent only. Okay, from linear transformation we can get a matrix, from matrix we can get a linear transformation. Here null space of A means set of all x value. For example, if A is a here A is a 5 by 3 matrix. A is 5 by 3 matrix. So x should be equal to 3 by 1. Okay, so this AX should be say 5 by 1. Okay, now the collection of all 3 by 1 x, that is x1, x2, x3, such that a x1, x2, x3 equal to 0. More specifically, set of all x1, x2, x3, that is set of all elements from R3 such that A 5 by 3 matrix into x1, x2, x3 equal to 0, the 0 matrix. Okay, 5 by 1 matrix. Okay, so this collection is called the null space of A and its dimension is called nullity. Okay, so this is same as the case in the linear transformation, and we have the result rank of A plus nullity of A equal to number of columns. So we have seen what is the maximum possibility for rank of A. It is 3. Obviously we have seen rank of A is less than or equal to 3. It can be 3 also, 2 also, 1 also, or 0 also. But maximum possibility is 3. So what should be the minimum possibility for nullity? Question is maximum largest possible for rank and smallest possible for nullity. Largest possible value we got 3. Now using this equation, can you say what is the smallest possibility of nullity?
0.
Very good, 0. Because rank is 3. Okay, that is the maximum possibility. And number of columns is 3. 5 by 3 means number of column 3. Correct? Number of columns of A. Okay. Now, so here what should be the value? 0. Okay, since this is the maximum, this should be the minimum. That is the combination we will get it. Correct? So 3 and 0 are the values required. Fine. Okay. So that is our question. So I hope that is also clear. Now, if lambda is an eigenvalue of A, prove that lambda square is an eigenvalue of A square. Actually, for eigenvalue we have like some other kind of definition also, but as of now you just know eigenvalue is the like root of the characteristic equation or characteristic polynomial. Correct? Now, the question is to prove if lambda is an eigenvalue of A, lambda square is an eigenvalue of A square. First we will see what is the given statement. Given statement, lambda is an eigenvalue of A. That means lambda is a root of the polynomial. We just know the polynomial. Determinant of A minus xi. It is just a polynomial. We are not equating to 0. Okay. The polynomial determinant of A minus xi. Okay. And we know lambda is a root of this polynomial. Correct. Now, since lambda is the root of this polynomial, what we will get? Determinant of A minus lambda should be equal to 0. Okay. For example, 1 is a root of x minus 1, something like that, x minus 1 square or something. This is a polynomial, we are not equating to 0. Okay. Now, it is a root means 1 minus 1 square equal to 0. Okay, what we are doing, instead of x we are substituting 1 here. Okay, So we have the polynomial here, determinant of a minus xi. It is a polynomial in x. And we got lambda is a root of this since lambda is an eigenvalue. So what we can conclude, determinant of a minus lambda equal to 0. Okay, that is how we are finding the eigenvalue. Equate determinant of a minus xi is 0. Find what are all the lambda. Here we have lambda eigenvalue. So we are saying that satisfies the characteristic polynomial. Okay. Now we need to find eigenvalues of a square. So what is the question? What is the eigenvalue of a square? So some x, if x is an eigenvalue or some value is an eigenvalue, means it should satisfy the characteristic polynomial of a square, right? What is the characteristic polynomial? A square is determinant of a square minus xi equal to 0. Again, a square is a matrix, not 0. Just polynomial means determinant of a square minus xi. What does that mean? Characteristic polynomial of a square means determinant of a square minus xi. Now, if lambda square is an eigenvalue of a square, instead of x, we should be able to put lambda square and we should be able to prove determinant of a square minus lambda square I equal to 0 if lambda square is an eigenvalue of a square. Okay, just as earlier case, this is a polynomial in x. Okay, then lambda square is a root of this polynomial if lambda square satisfies the equation determinant of a square minus lambda square I equal to 0, that is substituting lambda square instead of x. Okay, now we need to prove this is true or not. To prove that, okay, this is what we want to prove. Now consider a minus lambda I into a plus lambda I. What is this? This is a square minus plus a lambda I minus a lambda I, it will be cancelled, minus lambda square I. Correct? Now, if we are considering determinant of a minus lambda I into a plus lambda I. In one side, okay, we are just doing determinant of, we are just applying like here in this equation LHS and RHS are equal. So obviously their determinant should also be equal to same value. Okay, they are equal matrix, same determinant. Now determinant of AB we know, determinant of A into determinant of B. That is determinant of A minus lambda into determinant of A plus lambda I, which is equal to determinant of A square minus lambda square I. Now, what is LHS? We have determinant of A minus lambda I into determinant of A plus lambda I. But we know this value is 0 since lambda is an eigenvalue of A. Okay, so 0 into some value. We don't need to check about this value. Whatever it is 0. LHS is 0. So, 0 equal to determinant of A square minus lambda square I. So, that is what we wanted to prove here, right? Correct? We wanted to prove lambda square is an eigenvalue, means lambda square satisfy this equation. It is satisfied now. Okay? Determinant of A square minus lambda square I equal to 0. That implies lambda square is an eigenvalue of A square. You may seem a bit complicated, like it is a kind of trivial one, but when we prove it, we need to solve the steps. Okay? Is that fine for everyone? Is the question any doubt in the proof? How we are like proceeding from lambda is an eigenvalue of A, we are obtaining lambda square is an eigenvalue of A square. So every stage we are using the given condition, correct? So anyone have doubt in this proof or anywhere?
No.
Okay, good. Okay, then we will go to the next question. Next question is to prove the matrix A and A transpose have same eigenvalues. Okay, this is also a very trivial thing. First thing, what is the characteristic equation of or characteristic polynomial of A? Characteristic polynomial of A means determinant of A minus xi. What is this basically? We are finding the matrix A minus xi and find what is the determinant. Okay. Now, determinant of A equal to determinant of A transpose. That you know, right? Like means determinant A transpose means just the exchange of row and column. So, if we are finding the determinant along the rows, in A transpose we will be doing along the columns. Whatever the value we can expand through any column or row. Okay. So, obviously determinant of A and determinant of A transpose are equal. Now, what is this? Determinant of A minus xi transpose, because A and A transpose have same determinant. So these two are equal. Okay. This is same as determinant of A transpose minus xi. Correct? Now what is this? This is nothing but characteristic polynomial of A transpose. Okay, xi transpose is again xi. So this is the characteristic polynomial of A transpose. What we got? Characteristic polynomial of A and characteristic polynomial of A transpose are same. So both are same polynomial. So basically their roots are also same, right? That is what we want to prove. What is the roots of characteristic polynomial? They are the eigenvalues. Since A and A transpose have same characteristic polynomial, they will have the same roots. That means they have same eigenvalues. That implies A and A transpose have Is it clear? Any doubt in this question? Okay, so yeah, please ask if you have any doubt. These are all just the concept. We are just like writing like different ways, but it is all some basic concept. Okay. So this question we have already done. Now again it is a very trivial question to find the value of x and y such that the rank of this matrix is 2. For that, what we need to prove? Maybe you can do simultaneously with me so that you can also find and get what is the value of x and y. So practice various problems so that you will find that like the subject will be easy for you then. So this is our matrix. What we need to do is reduce it to maximum possible form. Here the 2 1th entry is 0. So no need to change the row R2. So we need to change R3 to R3 minus 2R1. Now, okay. From here you may be, the question is like find the value of x and y such that rank of the given matrix is 2. Okay. Now let me ask two questions. X equal to 2, y equal to 4, x equal to 3, y equal to 4, and x equal to okay, that's enough. Okay. Now, in the first case, x equal to 2 and y equal to 4. What will be the rank of A? Yeah, rank is 2. So that is basically what we want. We want x and y such that rank is equal to 2. Now the next question is x equal to 3 and y equal to 4. In that case, what is the rank? 2, correct. So just by like seeing 3, you may think there is a non-zero entry in the third row, and we may suddenly conclude that rank is 3, but that is not correct, because here this x minus 2 can be further reduced. So that is what we are going in to do in the next step. 0 1 0 0 0. What we are doing, R3 is changing to R3 minus x minus 2 times R2. Okay, so that value can also be made into 0, but whatever we are doing operation, y minus 4 remains the same. So in this case also rank is 2. Okay, now if x equal to 3 and y equal to 1, what will be the case? Okay, or what we can do is, from here what we can conclude, x can be any value, right? Okay, whatever the operation we are doing, finally we can like completely remove x from this matrix, final matrix. So x can be any value, whatever it is x, we will get rank is 2. The only condition is on y. Y should be equal to 4. So in this case, what will be rank? No, this case rank will be 3, right? Y is 1
Uh,
is,
for for option C, rank 3.
yeah, rank 3. Because y should be 4. We cannot change the y value. Y should be 4 in order to have rank equal to 2. Okay. So x does not matter. X can be 2, 1 or whatever the real number. Y should be equal to 4. Okay. Now let's go to the next question. This is also just the concept only. A is an n by n invertible matrix. Okay. Which of the following is true? First question is the homogeneous system. Homogeneous system means Ax equal to 0 form. That means the like RHS is 0. Okay, if it is non-zero, it is non-homogeneous or inhomogeneous. So homogeneous system means Ax equal to 0. The question is Ax equal to 0 has a non-trivial solution given A is an n by n invertible matrix. And the second one is system Ax equal to y has a solution x for every y, for every n by n, for each n by 1 matrix y. Out of this, which one is true or which one is false? That is the question. First, let us see the option A. Can anyone comment on A? Is this true or false? Does it have a non-trivial solution or not? If yes, what can be the solution? Or if no, we need a proof. Okay. See what is the given condition and check what is the possible solution. Non-trivial solution means a non-zero solution. That is the meaning of non-trivial solution. Trivial solution means only zero solution. Obviously, Ax equal to 0 has a zero solution, right? Whatever the matrix A, okay, we can multiply with 0, 0 column, and we will get 0, Ax equal to 0. So x equal to 0 is always a solution for Ax equal to 0. The question is not about the zero solution. The question is about non-zero solution. That is the meaning of non-trivial solution. Does there exist a non-trivial solution for Ax equal to 0 when A is an n by n invertible matrix? how you can use the invertibility. That is what you want to think. Okay, the only condition here is A is an n by n invertible matrix. How you can use that? A is invertible, we have A inverse. How we can wisely use the A inverse to find the solution? Okay, suppose obviously 0 is a solution. Now I am assuming x is a solution. I don't know whether it is 0 or non-zero. Okay, I am taking x is a solution of Ax equal to 0. So our intention is to check whether x can be non-zero. Okay, now we know x is a solution of Ax equal to 0. That means A into this x, given x is x equal to 0. Or for example, let me take x star or something. Okay, to understand, like x star is a particular solution, Ax star equal to 0. Now, Ax star equal to 0 means A inverse Ax star equal to 0. That means here also we have some 0 only, right? Okay, Ax star is a 0 matrix. If we are multiplying with the A inverse also, obviously it is again a 0 matrix. Correct? Now, what we can do? A inverse A. What is A inverse A? It is identity. That is Ix star equal to 0. That implies Ix star means x star. So, I am starting with some particular solution. I don't know whether non-zero or 0. But I am ending that x star is 0. So, what I am getting? X star is the only possible solution. That means x star equal to 0 is the only possible solution. So, using the invertibility, what we are getting? A inverse, Ax equal to 0 means it has only 0 solution. Clear? Now, what is the solution then? What is this? Okay, that is enough. X equal to 0 is the solution. Yeah. Correct? Is this clear? So, what is the first statement? Homogeneous system has a non-trivial solution. So, it is false. Because we got whatever solution we are taking, we finally ending up on it is a 0 solution or a trivial solution. So, it does not have a non-trivial non-trivial solution. Is that fine for everyone?
Yes, ma'am.
Okay. Now in the same way you can see B option. Okay, B option is given Ax equal to y. The system is say x equal to y. Fine. Now the thing we need to prove or disprove is the system Ax equal to y has a solution x for each matrix y. For each n by 1 matrix y, it has a solution. Again, A is an invertible matrix. Is this true or false? If it is true, we need to give what is the solution. If it is false, we need to find a y for which there is no solution x exists. Clear? Just think in the same way as we did in the A part. Now, tell whether B is true or false. Means if we are having Ax equal to y, we already have seen we will consider augmented matrix Ay. Correct? If rank of A and rank of Ay are different, then it will not be having a solution. Okay. But in this case, we are having A is an n by n invertible matrix. So that is what we want to use here. So, whether it has a solution in this case. In general, Ax equal to y need not have a solution when y is non-zero. When Ax equal to 0, it always has a solution which is called trivial solution. It can have more solution also depending on A. Okay. Now, the system Ax equal to y need not have a solution. It actually depends on y and the A in general. Okay. But in this case, given A is an n by n invertible matrix, and the question is whether Ax equal to y has a solution for any y. What we can do? Use the invertibility. Using the invertibility, can anyone tell? What should we do here? How we did in the earlier case, just like that. A is invertible means A inverse exists, right? So this implies we can multiply left with A inverse. Okay, y is an n by 1 matrix, A inverse is also an n by n matrix. So A inverse y is well defined. Okay, now here it becomes A inverse A is identity, so left side becomes just x. X equal to A inverse y. What we want to find? X value, correct? X is the solution. Whether such an x exists, that was our question. So x is A inverse y. Whatever we are choosing y, multiply the left side with A inverse, then that value will be a solution for Ax equal to y. What we are doing? X is A inverse y is a solution. Why it is a solution? If we are substituting in the equation 1, what we will get? Ax. What is our x? A inverse y, which is y. Correct? Ax equal to A inverse y, which is equal to y. So what we got? A inverse y is a solution. So whatever the y we are choosing, if A is invertible, A inverse y is a solution of Ax equal to y. So always we have a solution in this case. So this statement is true. Clear for everyone? Any doubt in this one? Anyone has doubt?
No.
Okay, very good. Okay, the next problem is also to find the rank of the matrix. That is just a calculation. Maybe I will very quickly do this. Suppose this is A. A is equivalent to 1, 4, 8, 2 minus 2. So what we will do here? R2 changes to R2 minus 2 R1. And R3 can be like this only. So again we can see R3 is a multiple of R2. Here R3 changes to R3 minus 2R2. So you can do the calculation here and the rank is 2. Because we have 2 non-zero rows in the row reduced form. So rank is 2. So like this we have done the questions earlier. So we can skip it now. Okay. Now again A is a 3 by 3 matrix satisfying A cube minus A square plus A minus I equal to 0. So we can say it will be the characteristic equation of the given matrix. The question is, what is A power 4? Whether it is 0 matrix or the identity matrix or A or like anything else. How can we find A power 4? We don't know what is A. They have just given A is a 3 by 3 matrix and they have given an equation which is satisfied by A. We need to find what is A power 4. Can anyone tell how to approach this problem?
A cube equal to A square minus A plus I.
What we can do? A cube equal to A square minus A plus I. From the equation we are taking A cube one side, all other. Now what we will do? multiplying with a on both sides, right? With a we can multiply both sides. So what we will get? A cube minus a square plus a. Now what is the thing? How you can use the given equation? What is the answer?
Is identity matrix.
Yeah, this is identity. What we are doing, we are just using the equation again. From here, if we are considering a q minus a square plus a in one side, we can take the identity to other side. So that is what we got here, right? So this is identity. Okay. So a power 4 is identity. So B is the option, correct option. Okay. Okay, and yeah, can you say what is the inverse of A from here? What is A inverse? No need to go to the equation. We got the a power 4 equal to identity. From this maybe you can conclude very quickly what is inverse, right?
A cube matrix.
Obviously a cube should be the inverse because we know a power 4 means a into a cube which is equal to identity. Or the same way we can write it is a cube into a. If we are able to write like this with any matrix whatever, it should be the inverse, this a cube. Okay, a cube should be the inverse, a inverse. Okay, so we can find like so this is the usual way of finding the inverse using the characteristic equation. Usually we will get a characteristic equation, so you can take, or from this equation also actually you can find it. Okay, from this also you can find it, you can keep I to one side and take all other things to other side and multiply with the A inverse, and you will get, for example, I equal to a cube plus a square, a cube minus a square plus a cube minus a square plus a. This is identity. Okay, so if we are like suppose a invertible, then what should be a inverse? We are multiplying a inverse with I. Okay, on both sides we are multiplying a inverse, so it should be a square minus a plus I. Okay, so a inverse is a square minus a plus I. Again, from this equation, a square minus a plus I. This should be equal to a cube, right? If we are taking this to other side, it is equal to a cube. So from here also we can write it is equal to a cube. Okay, so usually like both are correct, in both way you can write it. So usually we will use characteristic, otherwise like for 3 by 3 matrix and all, to find the like inverse is a bit difficult. We need to find adjoint, determinant, and those procedure takes like lots of calculation. So this is a better way to find the inverse using the characteristic equation. Okay. Okay, now this is again a very simple question. You can answer very quickly. Rank of the singular matrix of order 5 can be at most what? Order 5 means a 5 by 5 matrix given it is a singular matrix. That means singular means determinant is 0. Singular means determinant is 0, and non-singular means determinant is non-zero. So what is the answer to this question? Rank of the singular matrix of order 5 can be at most means maximum value.
4.
Yeah, 4. Obviously it cannot be 5. If it is 5, that means it is determinant is non-zero. Okay, that means it is non-singular. Correct? So it can be 4 only. Maximum answer is 4. Answer C. I hope the concept is clear for everyone, because we have seen this kind of questions so many times. So like I am not going to explain more and more on this, or if you want me to explain, please tell me, I can explain again. So at most 4, it can be 3, 2, 1, 0, whatever, but it cannot be 5. Okay. Okay, this we have done already, right? No, this we didn't do. Okay, we have proved that eigenvalues of A and eigenvalues of A transpose are same. That we have proved. Here the question is rank of A and rank of A transpose are same. This is actually maybe just by intuition you can like guess rank. Either we will find it through the row reduction or the column reduction, right? So A and A transpose are just row column exchanging. So it is actually the same way. One is doing through row, one is doing through column. That only the difference. Obviously it should be true. So if we are writing it in a proper way, how we will write it? What is rank of A? Rank of A is same as row rank of A. Okay, rank of A, row rank of A, column rank of A, everything same. Okay, rank of A means we know, reduce it. Row rank means it is same, like what is the dimension spanned by the rows. Row considering as a vector, what is the dimension spanned by row. This is same as rank of A, which is same as column rank of A. That we have seen in the class. Rank, row rank, column rank, all are equal. Okay. Now what is column rank of A? It is basically the row rank of A transpose, right? Row rank of A transpose. What is column rank of A? Column rank of A means the subspace. This is the subspace generated by rows, and column rank means subspace generated by columns. That means the columns take all the linear combination, and what is the subspace? That is the column space or column rank. Okay, I mean that is the space, and column rank means the dimension. Okay, let me be clear. Dimension of subspace. Okay, this is a value. Subspace means a space. Dimension means the row rank. Okay. Okay. Now subspace generated by column of A, which is same as subspace generated by row of A transpose. Correct? Because row and columns are interchanged in case of A and A transpose. So row rank of A transpose, or the subspace generated by columns of A, is same as subspace generated by columns of A transpose. So column rank of A is same as row rank of A transpose. Now again row rank of A transpose is same as rank of A transpose. Okay. This is just by intuition only. We can tell how it is coming, because one is doing through row reduction, one is doing through column reduction. Like both will finally give the same rank. Correct? That's all. Fine for everyone? Okay, let's move to the next problem. Which of the following is true? Rank of AB equal to rank of BA, rank of AB equal to rank of A transpose B transpose, rank of AB equal to rank of B transpose A transpose. Like just from the previous question, one thing you can quickly tell which one is true. Like only one option is true. Use the previous one. Previous one what we used, the rank of A and rank of A transpose, both are same. So using that one, you can conclude which option is correct in this. Anyone?
C.
Yeah, C. Very good. Because rank of AB will be equal to rank of AB transpose. Because A and A transpose. And transpose are same rank. So AB and AB transpose have same rank. Okay. like while doing transpose thing, what we will get? AB transpose is B transpose A transpose. So we are using this result. So rank of AB transpose is rank of B transpose A transpose. Clear? So option C is okay. Now the next question is rank of okay. Now we need to check the A and the B option. What about A and B? Rank of AB and first of all, whether AB, BA are defined actually. I mean, if AB is defined, BA is also defined or not. Suppose AB is defined, when will BA be defined? Suppose A is 2 by 3, B is 3 by 4. Okay. Now AB is defined, but BA is not defined, right? 3 by 4 into 2 by 3 matrix. That is not possible. We cannot like do the operation BA. BA not defined. So basically the question is like not even a logical question. I mean rank of AB, rank of BA. If it is not defined, we don't know. Like we cannot find the rank because BA does not even exist. So that is not true. And rank of AB and A transpose, B transpose. Here also if we are considering A transpose is a 3 by 2 matrix, B transpose is a 4 by 3 matrix. Here also A transpose, B transpose not defined, AB defined. Okay. B transpose, A transpose is always defined, AB all transpose. Okay. But A transpose, B transpose need not be even defined, well defined. Okay. So in this case also, the rank of A transpose, B transpose we cannot find actually, basically, because it is not, need not be defined always. So the second one is also false. Now we will come to one question. A and B are n by n matrices. Both are n by n means AB is defined, BA is defined. Okay. Now the last question, okay, we completely removed that question because we don't even know whether BA is defined if AB is defined. Okay. Now the question is both A and B are n by n matrices, so we cannot say AB, BA are not defined. Obviously A and B are defined, AB and BA are defined. Now in that case, what do you think? Rank of AB equal to rank of BA or not? If they are same, what we need to prove? Like we need to prove the result. Otherwise, you can find some counter example A and B such that AB has some rank, BA has different rank. So okay, I will give you one hint. Actually this is false. If A, B, BA are defined, rank of AB and rank of BA need not be equal. Okay, consider some 2 by 2 matrices, the simplest case, A and B. So I am asking you to find, okay, you can just think now itself, find two simple matrix A and B. Okay, it's like very simple matrix you can find, such that AB has one rank, BA has one rank. I mean AB has like the value rank AB, rank BA are distinct. Okay, the thing is this is false statement. I am asking you to find a counter example to say this is a false statement. For that what we want? Rank of AB not equal to rank of BA for some matrix A and B. For that you can start with a very simple matrix A and B, any simple matrix. First of all, my question is, can you take A and B as invertible matrix? If A and B are invertible, or okay, you leave that, we can discuss later. Just give me two matrix A and B such that rank of AB not equal to rank of BA. Like try for some 2 minutes, take some 2 by 2 matrices. I suggest you to take a non-invertible matrices, A and B as non-invertible matrices, so that if it is invertible, obviously we are going to face some problem. Again, maybe I will give one more hint. Take both matrix A and B with rank 1, but they are not equal. A and B are different matrix. Both have rank 1, such that the product AB is a non-zero matrix and BA is a zero matrix. Okay, AB non-zero matrices. Product, either the product AB or BA. One of the product is a zero matrix, so that we will get rank 0, and the other matrix is a non-zero matrix, like other product is a non-zero matrix, so we will get rank 1, like that. Please try this for the next 1 minute. If you are getting the answer, please let me know. Anyone? Anyone have idea, or are you trying? Or if you, okay, you can just take some like trial and error method, just try with 1 or 2 matrices, like for that AB is rank 1, BA is rank 0, something like that. If you are trying, or do you want some more time to try, or can I write now? I don't know whether you are trying there or not. Okay, I think I can write. Okay, if you want to try for some time, please let me know. Otherwise, I will write the matrices, and we can see how AB and BA will come and how we are choosing the matrix A and B. Suppose A I am taking as 1 0 0 0 and B is 0 0 1 0. Okay, what is rank of A? What is rank of A and rank of B?
One.
Yeah, both rank is 1. Okay, that you can like easily see, because only one non-zero row is there and we cannot reduce it further. And what is AB?
Zero matrix.
Yeah, zero matrix. Now what is BM? 0 0 1 0, right? Correct? AB is zero matrix, BA is non-zero matrix. So rank of AB is 0. For zero matrix, rank of AB is 0 and rank of BA is 1. Okay, here AB, BA both are well defined, but still rank is different. Right? Is that fine for everyone? Okay. The reason is we have taken A and B suitably such that they have rank 1. Now, if both the A and B has rank 2, then it will not work actually. What is this? A and B has rank 2 means determinant of A is non-zero and determinant of B is non-zero, right? In that case, determinant of AB is non-zero and determinant of BA is non-zero. What is determinant of AB and determinant of BA? Determinant of A into determinant of B. Similarly, determinant of B into determinant of A. Both are non-zero. What does that mean? AB and BA has full rank. That means rank AB equal to rank BA. Okay, so when we are going for the trial and error method, we should have an idea like what kind of things. If we are taking the full rank, it is not going to give something. I mean, always going to be rank AB, rank BA equal. So that is why we are going to choose suitably with the lesser rank. Okay, like that you should think and approach a problem. Okay, you should have an idea where it is actually where it is not working. So when you are going for a counter example, think like this and go for a counter example. Okay. Okay, here, okay, it is a very simple thing. This also we used the result earlier using that. A is a 3 by 3 matrix. A is a 3 by 3 matrix with given trace is 5 and 2 eigenvalues are given 2 and 3. Since it is a 3 by 3 matrix, we will have 3 eigenvalues obviously. Out of that, 2 eigenvalues are given 2 and 3. The question is whether A is invertible or not. Just using the result, trace is sum of eigenvalue and the determinant is product of eigenvalue. You can say whether A is invertible or not. First I will suggest you to find what is the third eigenvalue. What is the third eigenvalue here? Let x be the third eigenvalue. Now what we know, sum of eigenvalue should be trace, right? So what are all the eigenvalues? So 2, 3, x are eigenvalues of A. Now can you say what is x?
0.
Very good. Sum of eigenvalues should be equal to trace. That means 2 plus 3 plus x should be equal to, trace is given 5. Okay, trace 5. That implies x equal to 0. Now, is A invertible?
No.
Yes. Reason is, we know determinant of A is product of eigenvalues. We are just using these two results, sum of eigenvalue trace and determinant of like product of eigenvalues determinant. Okay. So what is this? 2 into 3 into 0, which is 0. So determinant is 0 means it is not invertible. A is not invertible. Okay, so question, is A invertible? No. Okay. Okay. Now maybe we will do this question. A is a 2 by 2 matrix with eigenvalues 2 and 3. Then question is, what are the eigenvalues of A plus 4i and what are the eigenvalues of A inverse? Anyone knows? I mean, if you have studied some kind of result, then you may be knowing these things, how to find very quickly the eigenvalues of A plus 4i. Okay. It is not so trivial result, so we can see how it is working. What we know, A is a 2 by 2 matrix and the eigenvalues are given 2 and 3. Okay, that implies 2, 3 are roots of the polynomial determinant of A minus so we have a polynomial or determinant of A minus xi. Okay, the characteristic polynomial. The eigenvalue means their roots. So 2 and 3 are the roots of the polynomial determinant of A minus xi since they are the eigenvalues. Now, what does this mean? Determinant of A minus 2i equal to 0. Okay, and determinant of A minus 3i equal to 0. Clear? Since they are the roots, if we are substituting 2 and 3 instead of x, we should get this polynomial should be equal to 0. Correct? Now, what we want to find? A plus 4i. Now, we need to find for which values, like which values will be the root of A plus 4i minus xi equal to 0. That means, let me write determinant of A plus 4i minus 2i plus 4i. Okay, we are considering this value. Okay, minus 2i plus 4i. Okay, so obviously from this 4i will get cancelled. What we will get? Determinant of A minus 2i equal to 0, because we know from the earlier equation determinant of A minus 2i equal to 0. Now, what is this actually? This is determinant of A plus 4i minus 6i. Correct? Now, this is in the form of determinant of A minus xi form, right? So, what we need to find? Eigenvalues of A plus 4i. Okay. So, what we got? Determinant of A plus 4i minus some 6i equal to 0. That implies 6 is an eigenvalue of A plus 4i. Is that clear for everyone? It is just a rearrangement. Okay, we got one eigenvalue. Now, what is basically the 6? 6 is nothing but 2 plus 4. 2 is an eigenvalue. From there, we are getting 6 is an eigenvalue. So, what is that? This 2 plus 4. That is the eigenvalue 6. That means eigenvalue of A plus 4i. That means that 4. Okay. In the same way, can you say what is the next eigenvalue? Corresponding? Yes. What is that? Corresponding to 3, what will be the eigenvalue?
7.
Yeah, very good. 7. 7 we will get. For that also you can do. I am not going to do that. Similarly, 7 is the eigenvalue of A plus 4i. Again, A plus 4i is a 2 by 2 matrix. Maximum 2 eigenvalue it can have. We got both the eigenvalues 6 and 7. Okay. So, actually this kind of result will hold for all kind of polynomial. Okay. So, I am doing for particularly this one. Now, what are the eigenvalues of A inverse? Next question. So, this also you can do similarly in the earlier case. I am not going through the calculation. Now, the second question is eigenvalues of A inverse. Can you guess what can be the eigenvalues of A inverse? Just like A plus 4i case, we know we were just doing the same kind of operation there, right? So, in the same way, first of all, A inverse exists because A is a invertible matrix. Here A has eigenvalue 2 and 3. So, determinant is 2 into 3 equal to 6. Okay. So, A is invertible obviously. So, A inverse exists. Now, what can be the possible eigenvalues of A inverse? think about the eigenvalues of A. So what is the eigenvalue of A inverse? Any guess? I'm not just asking like your guess, just like A plus 4A guess, what can be for A inverse? So we can guess it can be 1 by 2 and 1 by 3, right?
Yes.
It can be 1 by 2 and 1 by 3. That is our guess. So let us see how we can work on it. So what we know? Determinant of A minus 2i equal to 0 and determinant of A minus 3i equal to 0. So only one case we will do. Corresponding to 2, we will prove 1 by 2 is an eigenvalue of A inverse. In the same way, we can prove 1 by 3 is an eigenvalue for A inverse. So here, determinant of A minus 2i equal to 0. From this, I am writing determinant of 0 equal to determinant of A minus 2i. From this, I should bring somehow the A inverse. Okay. How I can bring A inverse? I can take A outside. If A taking outside means I will obtain I remaining and 2 times A inverse. Okay, I can write like this. Fine. Now what I want is when we will do for A, we will write determinant of A minus 2i. So for A inverse, it should be something like determinant of A inverse minus some xi, something like that, right? So what we can do is determinant of A, and this minus we can take outside. So minus 2 I am taking outside. Minus 2. Minus 2 is just a number actually. Others are matrix. So A inverse minus half I. Okay, if I am taking minus 2 outside corresponding to A, I, the quotient will become minus half. Now we are doing, what is this coefficient minus 2? If we are taking outside it, minus 2 square, minus 2 power n we will get, right? When we are finding determinant of something like this, into determinant of A into determinant of A inverse minus half I. Okay, so now see the left side. Left side it is 0. This is obviously non-zero. Okay, and determinant of A is also non-zero because A is invertible, we know. So determinant is non-zero. And only thing remaining is determinant of A inverse minus half I. Since these two terms are non-zero, the only possibility is determinant of A inverse minus half I should be equal to 0. Is that fine? What does that mean? Half is an eigenvalue of A inverse. Eigenvalue of A inverse. So we are starting with 2 is an eigenvalue of A. We obtained 1 by 2 is an eigenvalue of A inverse. Similarly, for this case also we can do, since 3 is an eigenvalue, similarly 3 is an eigenvalue of A. The same procedure you can repeat. Okay, take the A inverse outside, then take the minus 3 outside and repeat the process. Implies 1 by 3 is an eigenvalue of A inverse. Again, A inverse is a 2 by 2 matrix. It can have maximum 2 eigenvalue, and we got 2 eigenvalue, 1 by 2 and 1 by 3. So these two are the eigenvalues of A inverse. Clear? Any doubt in this question? So basically any kind of polynomial if you are getting, you can do that. Like for example, if x is an eigenvalue of A, x square will be an eigenvalue of A square. Okay. X square plus x will be an eigenvalue of A square plus A. Okay. In general that is true. Okay. I have done some simple small cases. In general also you can extend this to in general for a general polynomial. Okay. Okay, this is very trivial question. Maybe this question also we will do. Okay. The one more question we will do very quickly. Find a matrix with the determinant 0, trace is 0, but rank is non-zero. Can anyone tell such a matrix? You can think about a diagonal matrix. For diagonal matrix, it is easy to find the determinant, rank, trace, everything, right? So can you give a matrix with the determinant and trace 0, but rank is non-zero? Some diagonal matrix you can think. What we need, determinant should be equal to 0. Okay, for diagonal matrix, what is the determinant? Like just the diagonal product, correct? So obviously one of the diagonal entry should be 0. Okay, for example, I am taking this 0, 0, 0, 0, 0, 0, 0. Okay, what is the other two diagonal entry? I should have rank non-zero. Rank non-zero means at least one should be like some non-zero element. For example, I am taking this to be 1. Okay, now rank is 1. At least the rank is 1. It can be 2 also. It is not 3. So, now what should be the last entry here? The last condition is trace is 0. We satisfied other two conditions. Only remaining thing is trace is 0. Trace means sum of diagonal elements.
-1.
Which is -1. So for this trace equal to 0. What is rank? What is the rank of this matrix?
2.
Yeah, 2. So rank is a non-zero, trace is 0, determinant is 0. Okay. Now second question is, if rank is 0, A is identically equal to 0. Is that true or false? It is true, right? Rank is 0 means like we don't have non-zero rows. That means all rows are 0 rows. Rank is 0 means. If rank is 1 means at least one non-zero row is there. If rank 2 means at least 2 independent non-zero rows are there. So rank is 0 means A should be equal to 0. Okay. Now what about the converse? If A is identically 0, rank is 0. Correct, right? That is also true, right? A is identically 0 means like rank is 0 because A is a 0 matrix. It does not have a non-zero row. So obviously rank is 0. These two are just trivial results. So yeah, I think we can stop for today maybe. Other questions? Yeah. Is that fine? Any doubt in the today's class? Anyone? First doubt?
No, ma'am.
Okay. Okay, then maybe we can stop today and we will see the next week. Next week is the last week of the like session. So, okay, thank you all. We will see the in the next week. Good night.
Thank you.